Welcome back to lectures on advanced calculus for engineers, and this is lecture number 17, and we will be talking about maxima and minima. So, there will be 4 parts and this is part number 1. So, in this lecture I will be talking about the necessary conditions for the existence of maxima and minima, and there will be some worked problems. So, before we go to the necessary conditions, let me just introduce that what do we mean by local maximum, local minimum, and there are few more terminologies which needs to be cleared before we go for the necessary conditions. So, a function z is equal to f x y, we have already discussed such kind of functions of 2 variables. So, has a minimum or maximum. So, let me just introduce for maximum first. So, a function z is equal to f x y has a maximum at the point x naught y naught if at every point in a neighborhood of this x naught y naught the function assumes a smaller value than at the point itself. So, if there is a point and in the neighborhood of this point the function assumes smaller values, then we call that this is a point of local maximum. On the other hand, if the function assumes smaller values in the neighborhood of a point, the larger values in the neighborhood of a point, then we call this point as a point of local minimum in that case. So, in the neighborhood of that point the function is taking larger values, and then we call such points as the point of local minimum. So, the definition is clear from this text itself, and such a maximum or minimum, whatever the case is called relative or local. Yeah. So, the two terms are used, relative or this local maximum or local minimum. And this maximum and minimum values together, they are called extreme values. So, if we are using the word extreme values, that means those values may be the maximum or minimum. So, as a combined word for both, we use extreme values. So, for instance, here this is the surface for this function z is equal to 4 x square plus y square and exponential minus x square minus 4 y square. So, as you can see, so there are several points which one can easily identify from the graph itself, that for instance, this point here, it is a point of local maximum because the function is taking smaller values in the neighborhood of this point. Similarly, at this point as well we have the situation that it is taking a smaller value. So, this is also a local maximum, and here also function attains its local maximum, because locally we are verifying that this is a maximum or not, but it may happen that at some point the value of the function may be more than this point, but locally we have the maximum value of this function. So, in the neighborhood, at least that neighborhood may be very small, but in the neighborhood function is taking smaller values than at this point. Similarly, if we take a closer look at here, we can also observe that here this is a point of local minimum, or we call it as local minimum. So, here also the situation is that in the neighborhood of this point the function is taking more values than that. So, this is a point of local minimum. Well, so there is a term absolute or global maximum used in this connection, and the point there is that the smallest and the largest values attained by a function over the entire domain. So, in the earlier slide we were looking at locally, that how this function is behaving locally, but now we are talking about the smallest and the largest value attained by a function over the entire domain, and not only the domain including the boundaries. So, if for instance, we have the surface here f x y is equal to x square plus 2 y square, and this is the domain here x square plus y square less than equal to 1. So, the boundary is included in the domain. Then we have to also search whether the maximum is attained on the boundary or not. So, the boundary has to be checked along with the interior part of the domain, and then such a the smallest or the largest value, we call it as absolute or global minimum or absolute or global maximum respectively. So, if we have the smallest value attained by a function over the entire domain including the boundaries, if the boundary is included in the domain, such value we call a minimum, global minimum or absolute minimum, and the largest value attained by a function over entire domain including the boundary is called then absolute or global maximum. Well, in this reference we need to introduce now the critical points and the saddle points. So, what are the critical points? The point x naught y naught is called critical point, or sometimes we call it as stationary point of the function or of a function f x y. If at this point the partial derivative with respect to x is 0 and the partial derivative with respect to y is also 0. So, these two partial derivatives at that point must be 0, then we call such a point as critical point. Or sometimes when the function is not or these partial derivatives do not exist, in that case also we call them as critical point, because we have to also investigate those points for maxima and minima, because we will realize soon here that these points, the critical points, are those points where the local maximum or local minimum exist. So, these are very important points. We have to first collect all such points where the derivative is 0, and both the derivatives are 0, derivative with respect to x, the partial derivative with respect to y, and we have to also collect those points where these or one of the derivatives does not exist, or these both derivatives do not exist. We have to also collect those points, because it may happen that at that point we have that local maxima or minimum. Well, and a critical point where the function has no minimum or maximum is called the saddle point. So, that also will be discussed little later. So, as I said that these critical points will be the candidate for local maximum and minimum, but there will be some critical points where no maximum, no minimum exists, and then such points we call saddle point. So, we can also observe in this surface plot that here this is a this will be a critical point also in the evaluation. Next slides we will observe. Here this is also a critical point, here also will be a critical point, because with respect to x and with respect to y the derivative will be 0. Here also there will be a critical point, and there is a point here as well where the derivative with respect to x and derivative with respect to y vanishes. So, we will investigate those critical points, or how to investigate them mathematically, because in this visualization one can observe that this is a local maximum, this is also local maximum, and this is a local minimum. Here also we have local minimum, and at this point, as we observe here, that there is an increase in this direction, here also increase, and then the function value is smaller or are smaller in this direction. So, whatever neighborhood we pick here around this point, there will be some points where the function value will be more in the neighborhood, and there will be some points where the function value will be minimum or smaller than that point. So, such points are not a point of maximum or minimum, and these points will be called as saddle point. But here the discussion in this lecture is that how to find these critical points, and in the next lecture we will learn that how to identify whether a given critical point is a point of local maximum or it is a point of local minimum. So, coming to the necessary condition for a function to have extremum. So, this is an important result. Let f x y be continuous and have partial derivatives at a point p a comma b, then the necessary conditions for the existence of an extreme value we have already introduced that as a combined term we use for maximum and minimum. So, the necessary conditions for the existence of extreme value of it at this point p are. So, what are the necessary conditions? That means then only such a point can be a point of extrema when the partial derivatives with respect to x and partial derivatives with respect to y are 0. So, these two derivatives must be 0, then only we can think about finding out whether this point is a point of local extrema or not, but this is necessary condition. If these are not fulfilled, we should not check basically for those points about the existence of extreme value of the function at this point. So, the point P is a critical point, that is the definition we have already introduced for the critical point. So, a critical point is a point where these two derivatives basically vanishes, and we are talking about where the partial derivatives exist. So, these must be 0. This is the necessary condition, or what we in other words we say that if the point P a b is a relative extremum of the function, then P a b is also a critical point of f x y. So, this is again this is a necessary condition for the relative extremum of the function f x y, that this point should be a critical point. So, that means we have to first identify all critical points and then we will investigate those critical points only for local maximum or local minimum. We should not look for all other points than these critical points. How to get these necessary condition, that also we will go through quickly here. So, let this a plus h b plus k be a point in the neighborhood of the given point a comma b. So, we are investigating or we are finding out these conditions for local extremum, that this point P a b. So, the P will be a point of maximum. When this point will be a point of maximum? When this delta f the increment in f, when we have a point in the neighborhood here and minus we subtract the function value at a b. So, this delta f, so we are talking about the P will be a point of maximum, that means it is attaining the higher values than the values in the neighborhood. That means this here, this is higher. So, it will be a less than equal to 0, this will be less than equal to 0 for sufficiently small h and k, because we are saying that P is a point of maximum. In that case, this delta f which is written here has to be less than equal to 0, and similarly this will be a point of local minimum if we have this delta f greater than 0, because now for the minimum, that means this f a b is locally minimum, that means in the neighborhood the function is taking more values. So, that means this f a plus h b plus k minus this f a b will be greater than or equal to 0 for sufficiently small h and k, because there exists a neighborhood. So, this neighborhood may be very small, still we will call it a point of local minimum or maximum. So, what we have done here, we have taken a point in the neighborhood of the point P a b, where we are looking for these necessary conditions, and we realize that P will be a point of maximum is this delta f will be less than 0, and a point of local minimum if this delta f will be greater than 0. Well, so we expand this using Taylor series about this point a comma b. So, we have this function f a plus h b plus k in the neighborhood, and using this Taylor series we can expand this around this point a comma b. So, we have already seen the Taylor series in the previous lecture. So, this can be written as f a comma b plus this first order terms. So, h f x plus k f y at the point this a comma b, and then we have these higher order terms where we have h square, the f x x, 2 h k, the mixed order derivative plus k square, f y y plus and so on, the more terms will come. Now, we note that this delta f we are denoting by this difference here. So, we have this delta f is equal to h f a f x a comma b plus k f y a comma b and these higher order terms. So, for sufficiently small h and k, the sign of this delta f will depend on the sign of the first term. So, this is important to realize, and on the next slide I will give some example that how this is happening. So, here this delta f is equal to these first order terms in h and k, then we have here square terms in h and k. So, if we choose this h and k sufficiently small, why the sufficiently small word is coming, that is also that will be clear in the next slide. So, that the sign of this delta f will depend on the first the linear terms here, because does not matter how large these second order derivatives are, but this for sufficiently small h and k, because here we have the square terms, here also 2 h k, here also k square. So, does not matter that how large these values are here, the sign of delta f for very small h and k will depend only on the sign of this h f x plus k f y, the leading term, the leading linear term. Then we have the square term, then we have the cubic terms, those terms will be even smaller for very small values of h and k. So, one should note that the sign of this delta f will depend on the first term, the first linear terms for sufficiently small h and k, it will not depend on the second term. If for very small h and k this is positive, then the delta f will be positive, and if this is negative, the first term, the delta f will be negative, because these will be negligible for very small h and k. The sign will depend only on the first term, not on the second term. So, we have this expression for delta f. Since we are talking about the neighborhood, so for instance this is 0. So, all these points, let us say this is our neighborhood. So, we have just restricted here neighborhood, let h to 0. So, we have h to 0, that means we are here on along this y axis, we can still move around this in the direction of k by varying k. So, then if we let this delta s to 0, this delta f will be k into f y. So, still this delta f is the same as before, but we have fixed a point in the neighborhood in along this y axis. So, we have this delta f is equal to k f y, because this h we are letting to 0. So, this term will also vanish. So, we have this first order term here k f y, and then we have half k square f y y a b and so on, some more terms. So, again the same argument that the sign of this delta f will depend on the first term, because this is a linear term and here we have the quadratic term. So, for very small k, this is going to be very small, does not matter how large is your f y y, accordingly this k you have to choose a smaller one. So, there will be a neighborhood where the sign will depend only on the first term, right. So, if we because f y a b is some given point there. So, the sign will depend then on the k. If k is positive, the sign will be positive, if k is negative, the sign will be negative of this delta f, because that will depend only on the first term, not on the sign of the second term. Why this is happening? Just we can get the idea from this example here. So, suppose we have an expression h minus 1000 h square minus 2000 h cube. So, if we pick this h 0.1, the value of this expression is minus 11.9. So, h, the sign of h was positive. So, here, but we are getting as the negative sign for h. So, it is here at present it is not like the sign of h is the sign of the whole expression. Why? Because h is large, but if we make our h is smaller, okay, still it is a negative, but it is supposed to be the sign of the first term, which is positive. So, if we take a even a smaller h, again this is negative, because of these 1000, 2000, they are actually contributing to make it a negative, but no problem, we will go with smaller h even. So, 0.0001, and in that case we see that yes, now the sign is positive. So, what we realize that there will exist such a h where the sign of this term will depend only on the sign of the first term, this h, the linear term, because here we have the quadratic term, here we have the cubic term. So, they will not contribute much when h is really a small number. So, with similar argument, here we said that the sign of this delta f will depend only on the sign of this k f y a comma b, but it may happen that for a very small k this will happen, but does not matter. We are talking about the neighborhood, and that neighborhood can be very small for this existence or for the maxima, local minima or minimum, maximum or minimum. So, assuming that f y is positive, because this is something given, yeah. So, f y is evaluated at a b. So, it may be positive, it may be negative, we do not know, but it will be a fixed number. So, let us say f y is positive. In that case, this delta f will be positive if this k is positive, if the neighborhood you have picked in this positive direction, and delta f will be negative if you choose this neighborhood in the other direction. Similarly, if we assume that f y is a negative number, in that case we have a similar situation that delta f will be negative, delta f will be positive. So, if we are claiming that this point a b is a point of extremum, that means either delta f will be positive or delta f will be negative. When this is happen, this can only happen when this f y is 0, because if this f y is not 0, what we have realized that delta f changes its sign. Delta f is positive here for k positive, delta f is negative for k negative, it is changing sign. So, if this a b is a point of local extrema, in that case this f y has to be 0, there is no other way, otherwise this will change sign and it will not be a point of local maximum or local minimum. So, to have this a comma b a point of local extremum, in that case this f y has to be 0, and here we are getting this necessary condition basically, that if a b is a point of local extremum, then f y has to be 0, and similarly we will realize that f x has to be 0. So, now getting back to our main equation of this delta f, and now this time we will let this k to 0. So, all these terms having the k will be 0, and at the end we will get only this first term and the term having this h square. So, the delta f, and again assuming like f x is positive. So, delta f will change again sign, delta f will be positive for h positive, delta f will be negative for h negative, and similarly if we assume also that f x is negative, delta f will also change, again it will change sign depending on whether h is positive or h is negative. So, therefore, the function cannot have an extremum unless this f x is equal to 0. So, here we have seen that f x must be 0, otherwise this cannot be a point of local extremum. So, in this way we are getting these necessary conditions, that if this a comma b is a point of local extremum, then f x must be 0 and f y must be 0 at this point a comma b. So, the necessary conditions for the existence of an extremum at the point a b is that f x must be 0, f y must be 0. So, if f x at a b is not equal to 0 or f y a comma b is not equal to 0 or both are not equal to 0, in that case this point cannot be a point of local extremum. This is what we have seen by this simple observation. Now, getting to two problems. So, one is find the critical points of this function f x y is equal to x cube plus y cube minus 3 x minus 12 y and plus 20 is equal to 0. So, to find the critical point, what we need to do, we need to set f x is equal to 0. So, from here what we are getting 3 x square, then here it will be 0, then we will get minus 3 from there, and the f y. So, this is equal to 0, that will be one equation, and the second f y is equal to 0, we will get the another equation. So, here the f y will be 0 when 3 y square minus 12 will be 0. So, these are the two equations which we got after setting this f x is equal to 0 and f y equal to 0. From the first equation we got that x square should be 1, from the second equation we got x square should be 4. So, that means x is plus minus 1 and here y is plus minus 2. So, what are these critical points? The critical points are then, so plus 1, and then from y I can take also plus, then here minus 1, there again plus. So, all these points the derivatives will be 0, f x will be 0 at this point, f y will be 0 at this point, minus 1 2 also both will be 0, and then we can take here the 1 and then the minus 2 from there, here also both the derivatives will be 0, and this minus 1 and minus 2 here also both the derivatives will be 0. So, all those points where both the derivatives are 0 are called the critical points. So, by solving these equations simultaneously, here the case was that from one was only having x, the other one was having only y. So, independently we got these points there, that any plus 1 from here and plus 2 or minus 2 from here is a critical point. So, in this way we got these 4 critical points. So, the critical points are, by setting this these two equations we got there, and by solving these two equations we got the critical points plus minus 1 plus minus 2, that means plus 1 plus 2 plus 1 minus 2 minus 1 minus 2 and so on. So, these 4 points we have. If you draw this there, you will can also visualize this, that there will be a point here, there will be a point there, there will be a point here and here, where these derivatives are with respect to x and with respect to y are 0 basically these points. So, there are 4 critical points for this function f x y. Another problem. So, here we have to find again the critical points for this function, and again a similar process, that f x is equal to 0 we need to set. So, that means this x square minus y square, and then the derivative of e power this minus x square minus y square over 2, and then minus 2 x, 2 get cancelled, minus x, and then here the 2 x, and then again e power minus x square minus y square by 2. So, this is your f x. This e and this will be set to 0. So, e power minus this x square minus y square will not be 0. So, we can remove this from here. So, what we will get from here, we have the 2 x, and there we have minus x, and x square minus 1 is equal to 0. So, x, and then we have 2 minus this x square minus this y square term and is equal to 0. So, this is one equation we got. Similarly, the f y is equal to 0 we set, and we will get the another equation. It is a symmetry in x and y. So, similar, instead of x we will get just y there in the second equation. So, we have 2 minus this x square minus y square, x is equal to 0, from this f x is equal to 0, and for f y equal to 0 we are getting minus 2 minus x square minus y square into y is equal to 0. This is the second equation we are getting. So, now we have to solve these two simultaneously. So, from the first equation what we realize, so from this first equation what we realize, that either x is 0 can make this derivative 0, or x square minus y square is equal to 2 can also make this equation 0. From the second we get similar observation, that y equal to 0 can make this equation 0, and x square minus this y square, if this is minus 2, in that case also we can realize that this equation will be also 0. So, this is the situation here. Now, we have to just pick, let us say from the first equation we take x is equal to 0, and from the second equation corresponding we can take y is equal to 0. So, that is one. Then the second situation, so this is first situation, then in the second situation from the equation first we take x is equal to 0, and from the equation 2 then we can set our x equal to 0 here. So, we get y square is equal to 2, that means y is equal to plus minus root 2. So, these are also the points x 0 and y plus square root 2 or minus square root 2 one can take. The third situation, now from the second equation first we pick the y equal to 0 for instance here, and then from the first equation we will substitute here y is equal to 0, we will get x plus minus 2. So, these are also the points 0 and then plus minus square root 2. So, the plus 2 comma 0 and minus square root 2 comma 0. So, these 2 points are coming out of this consideration. Well, so these are the possible solutions now at all these points, whether it is a plus square root 2 comma 0 minus square root 2 comma 0, or we have the 0 comma square root 2 0 comma minus square root 2, or we have 0 comma 0. At all these points the function value the derivative value of this function will be 0 at all these points. So, what are the critical points? We have exactly what we have evaluated there, 0 comma 0, we have square root 2 comma 0, we have 0 plus minus square root 2. So, these 5, so we have 1 here, the 2 and the 2. So, there are 5 critical points of this function which one can also observe in this figure itself. So, there is a point here and there is a point there and again here and also here, and there is a point on this top which is also a critical point. So, in the direction of x there is no change, in the direction of y the equation is parallel to this y axis. So, here these are the 5 points, and as we can realize from the figure that this is a point of local maximum, this is also a point of local maximum, and these points here are points of local minimum, and at this point as we can see that the function is increasing in this direction, but decreasing in the other direction. So, it is neither a point of maximum nor a point of minimum, and therefore, this is called a saddle point. But this was just by this visualization, but in the next lecture we will see how mathematically we can find out or we can identify these points as the point of maximum, point of minimum, or the critical points. Well, just to conclude, so in this lecture we have learned these necessary conditions for extremum. By setting these two derivatives to 0, we will get all the critical points, and these are basically the necessary conditions for extremum. So, if a point a comma b is a point of extremum, then f x must be 0, f y must be 0 at that point. And these critical points are basically the candidates for local extremum, means the local maximum, local minimum, and also some of them may be saddle points. So, as we have seen just in the previous lecture, by this surface itself we could realize the points of local extremum or extrema and the saddle points. Well, so these are a few references which we have used for preparing the lecture, and with this I thank you very much for your attention.